Hello friends, welcome to section 7 of the Hard Surface Modeling series. This time we will be learning about curve modeling, and this will be the final section discussing new methods before we test all our knowledge with some modeling practice. Curve modeling is great when it comes to making objects like ropes, chains, and most importantly for hard surface modeling, wires. There are already some great tutorials on this topic, and as to not repeat their points, I will attempt to portray it in a unique way. Therefore, this tutorial will also include how to rig these curves. If you remember, in the first section I mentioned that if this series does well, and I see demand from you guys, I will make a similar, extensive tutorial on hard surface rigging, which would include a section on curve rigging in more detail. With that said, let's get into it by making some twisting wires. Step 1 is to create your base shape. In this case, since we only want basic wires, we can use a cylinder. In this workflow, arrayed objects can become very dense in geometry, so try to start off with a low poly shape. Make sure to remove the top and bottom faces so that the shape can seamlessly transition when in an array. We will look at how this first step gets slightly more difficult when our base shape is more complex in the next example. Step 2 is to array your object. Add an array modifier and make sure your instances are aligned. By default, the fit type is set to fixed count, but for this workflow, you might decide to change it to fit curve, which requires you to create and select a curve the shape will fit to. I will discuss the benefits and weaknesses of each fit type in a moment. Make sure to enable the merge option and tweak the distance if needed. Step 3 is to get our mesh to trace the path curve. To do this, add a curve modifier and assign the curve object. You might need to change the deform axis. It is important that the origin of your base shape is in its center and that the shape and curve have the same origin. Otherwise, there will be an unwanted offset between the shape and the curve. Those are the basic 3 steps, but I will show you how you can quickly spice up this mesh and add more detail. I'll go into edit mode, duplicate the shape and resize it, remembering to keep all cylinders the same length on the arrayed axis. Recenter your mesh if needed. This is already looking great, however there is one more thing we could do. Add a simple deform, place it between the array and curve, bring up the twist value, and change the axis if needed. If we look at the object one modifier at a time, the effects are clearer to understand. First, we array the object, then twist it, then place it on the curve and smooth it with a subdivision. Now let me explain the benefits and weaknesses of the array fit types. The main differences between the fixed count and fit curves options is that unlike the fixed count, the fit curve option will always adjust to you editing the curve. However, adding new geometry to fit the curve can lead to visual bugs when animating. To get the best of both worlds, you can choose the fixed count option for curves that you know will need to stretch a lot, making sure to hide some extra geometry, and when you want an accurate curve that won't move too much, use the fit curve option. You can always switch between them if you change your mind. Another thing to keep in mind, as mentioned, is to keep the base mesh low poly. However, you need to find a balance between the amount of geometry and the deformation quality. Less perpendicular cuts to the array axis may lower the quality of the curved mesh, even more so if you are using a simple deform modifier too. For each individual situation, decide how much quality you are able and willing to sacrifice in order to keep the mesh light. Now let's look at a more complex example, a chain link. The first step is to create the base mesh, making sure it will perfectly transition between instances. I would highly suggest you bring in some reference images for this. All you need is a simple reference that demonstrates the pattern of the object. In this case, the chain link can be isolated to this repeating pattern. I'll start by spawning a torus and lowering the resolution, then begin modeling. Notice I'm using increment snapping to make sure all my transformations are precise, and how my proficiency with modeling tools like mirroring using the Ctrl+M shortcut speed up my workflow. Now that I have one chain, I can duplicate, rotate and position it, before cutting it in half and mirroring to the other side. I will then inflate the mesh with the Alt+S shortcut until the chains are thicker. Now we can move on to the second step, arraying this into a repeating pattern, using the Fit Curve option and enabling the Merge option. Finally, we can add a curve modifier, and since the origin of the shape and curve are both in the center, it should work perfectly. And just like that, we have a chain link. It may not be as realistic as running a physics simulation, but this should be good enough for most situations. With the basics of curve modeling in our pockets, we can move on to learning about how to rig these curves. This technique includes a modifier for curve objects, which you might have come across, the hook modifier. The hook modifier allows you to bind specific points to objects, empties or bones. You can then move the objects, which will move any curve points hooked to that object. The first thing we need to do is create bones for our curve. This is a simple process. Just place the 3D cursor at the first point and spawn a single bone. Then place the 3D cursor at the next point on the curve and move the tail of the bone to that location, extrude another bone, and continue the process until you have covered the entire curve. To easily control the bones, I like to use an inverse kinematics constraint. To do this, we need to extrude another bone at the end of the chain to act as a controller, making sure to disconnect and unparent it. We also need to extrude a bone and place it around the halfway point to act as a pole, making sure to also disconnect and unparent it. In pose mode, select this controller bone, and then the next bone, and press Shift+I to assign an IK modifier to this bone, turning it yellow. Now when I move the controller, this chain follows. To determine the rotation of our chain, we need to assign the pole bone in the modifier. You will need to slightly rotate one of the bones in our chain, as well as needing to tweak the pole angle value. It doesn't have to be perfect. Once that is done, you can move the bones with the controller and control its direction with the pole. Next, we need to hook each curve point to a respective bone. First thing is to set the rig to rest position, which you should always do when parenting to a rig. Now select the first bone in edit or pose mode, then go back to edit mode, select the rig and then the curve, and go to edit mode. Select the first point and press Ctrl H, and hook it to the selected bone. Make sure you are also selecting the handles of each point. If you have trouble selecting the rig and then the curve, use the outliner. We need to repeat this process for each point on the curve. Select a bone, then select the rig and curve, then the corresponding point, and hook it. The last point on the curve should be hooked to the IK controller. After all that, we can finally control the curve with the controller and pole. Let's go over what is happening here. First, our object is arrayed and deformed to fit the curve. Then we take the curve and hook each point to a rig. Then, using an IK constraint to control the rig, we move the bones, which moves the hooked curve, which deforms our mesh. All this combined generates a streamlined curve-based workflow. Well done, we have completed all the content of this series. In the next, final section, we will test our knowledge of all the techniques and tools we have learnt by designing common hard surface objects. See you there. Remember to like and subscribe for more, and comment any thoughts or questions.